Hello, in this video we're going to take a look at Young's modulus. So this is the other thing in materials that people tend to think of alongside Hooke's law. Named after Thomas Young, the genius, the guy who could do everything. I've got a separate video on him. He's one of my favourites. So go and have a look at that if you're interested in that sort of thing. Now, why are we looking at Young's modulus? Up until now, we've been drawing a lot of force extension graphs. But these graphs, like a Hooke's law thing, we got them proportional to each other up to the elastic limit. These vary according to not only the material, but the dimensions of the material. So let's consider two ways this could change. So say we had two bits of rubber, say, that were the same length, but one of them was thinner than the other, and we applied the same tensile force to them. Which one is going to stretch more? Well, we'd expect the thin one to stretch more than the thick one. We know this from experience. If you've got rubber bands, the thin rubber bands stretch a lot more than the thick rubber bands for the same applied force. But then also, if we did have two thin rubber bands and we had a short one and a long one, both of the same thickness, and we applied the same force to those, well, we'd expect the long one to extend more than the short one. So we've got variations here. One of them is varying according to the area, and the other one is varying according to the length. So if we've got some way of removing these areas and lengths from our force and our extension, then we're going to be able to talk about the material and not the dimensions of the material. So that's what we're doing here with Young's modulus. So you might remember back in our definition, in our terminology video, I mentioned stress and strain, and stress was to do with force and strain was to do with extension, at least when we're looking at linear changes in dimensions of an object. We're just extending it in one dimension, we're pulling it in one direction, so we're getting an extension. But strain can be related to stretching in multiple dimensions or bending, twisting, or whatever. But at the moment, we're just thinking one-dimensional extensions. So we've got our force thing, which is stress. We've got our extension thing, which is strain. Now let's try and get rid of these areas and lengths on this, because we're saying here that when we're looking at the force applied and the extension we're going to get, it's going to vary according to the area. That's what we were looking at here. This is a stress related thing. So if we say that stress, rather than just having force, we're going to have stress, which is force over area, then that's going to be a good start. And then similarly with strain, because on this second example here, we were thinking, well, the extension, really, we want to quantify the extension as something to do with the original length of the material as well, because the longer materials will stretch more. Well, let's then take strain to be the extension divided by the original length. So we've divided these things out. And now we can plot these on our graph. Rather than having force against extension, we can have stress against strain. So we can do a stress-strain graph. Stress versus strain. This is our force divided by our area. This is our extension divided by our length. So now when, rather than what we had before, when we were looking at Hooke's law, and we were saying, okay, the gradient of this graph here, our F over X, is equal to our force constant K. Well, now if we've got our graph, and this is still going to be linear inside the elastic limit, because we've got a couple of constants here of the area and the length. So if we're looking at the gradient of this, the things that are changing is the force extension thing, which is going to be changing. The area and the length are constants for a particular object. So we're still going to get a straight line up until the elastic limit. But now our gradient is stress divided by strain. Stress divided by strain is going to be FL over AX, just dividing these together. This is often denoted with the Greek epsilon. And this is Young's modulus. That is Young's modulus here. So you can see how similar it is to our force constant that we were looking at previously, but we've tried to remove we've been removing the definitions or the dimensions of the object that we're looking at. So we're not just looking at force over extension, we've now taken out the area and the length of the particular object in order to have a material definition. What is the thing made of, and how can we describe that? So we're going to see similar properties here for Young's modulus as we are for the force constant. So yeah, if you've got aluminium or some other metal like that, then for a certain amount of pressure we're going to get, because this force over area, we're looking at a pressure here that's applied to material, we're not going to get very much extension, so we're going to get a higher value of Young's modulus in the same way as you get higher force constants. The newtons per meter are high for stretching aluminium compared to, say, stretching rubber, where for a particular pressure you're going to get a much greater extension. Everything else being equal, for the same Fa and L, you're going to get a higher value of X for the rubber, so you're going to have a low value compared to the aluminium. So we've got the same sort of variation going on here for Young's modulus as we have for the force constant, but now we're just looking at the material rather than its dimensions. Now, Young's modulus, you can't just have, this is how a material behaves in all directions, because a lot of materials have got some kind of grain to them. You think of carbon fibers and things like that. Anything which is fibrous in that way, you've got the difference between applying a force along the grain or across the grain. So depending on which direction an object is loaded in, you might get different Young's modulus for that. So it's not just the case of, here's a material, here's Young's modulus, off you go. It doesn't change. That's not the case. Right, let's round up on this bit then with Young's modulus of looking at a couple more graphs then. So let's look at some brittle materials. So if you've got brittle material and we're doing a stress-strain graph, so stress and strain, then the gradient is our Young's modulus. Well, I say the gradient is Young's modulus. That can be a little bit misleading. Let's just unpick that bit. Young's modulus isn't a gradient. It's a ratio of these two values. It's the ratio of stress versus strain. So if you've got a material which is perfectly Hookean and it's got this straight line period here inside the region of elastic deformation, then any point along this line, if you take the ratio of stress to strain, is going to give you Young's modulus. We will use the gradient to work out Young's modulus because it's a way of averaging essentially multiple values. You're not going to get these perfect measurements, the object, the material and its particular dimensions and such like. They're not going to behave perfectly as well. So you're going to get a certain variability just from that's how materials are. You might have, impurities or whatever in it. You might be approximating the Hookean period domain inside this extension, and then you've got the errors in your measurements. So we're approximating all of that and taking an average by looking at the gradient rather than Young's modulus actually being a gradient. It is a ratio. So it's a slightly subtle point on all of that. But that's what I mean by saying we're using the gradient in order to work out Young's modulus. If we've got brittle materials, then we might have something like, glass is brittle. So you're not going to get, I don't know how it's going to vary. I've got no sort of scale on here at all on the axes. But say you've got glass, it's going to stretch to some, we're thinking extension along here. We've got some kind of extension going on in our strain, but it's brittle as in it just breaks. You don't get this inelastic deformation bit which is going to happen somewhere else. You've got a tiny amount of give and then it's gonna snap because it's brittle. So this is what you get with the brittle stress strain graphs, that you sometimes you get the arrows on it that they're loading and unloading along the same graph. You've got a similar thing with a higher Young's modulus if you've got something like cast iron. So that's what happens with these brittle materials. The ones that are more involved are when you get the ductile materials. So yeah, there's loads of low carbon steel is the one they seem to want people to draw quite often. And we know what it can be like with steel. You see it where you get these obviously they can take higher loads, but you see the deformation in materials where, and you see it with steel, you know, where you get these thin points where you start stretching too much, and it really starts behaving in this plastic sort of way, doesn't it, when they're about to break. So this is the sort of inelastic deformation that you're going to get going on in these materials. And yeah, low carbon steel is a relatively ductile steel. It's a relatively ductile metal, unlike cast iron, which is much more brittle. And you get all manner of things going on in these stress strain graphs. So if this is our, again, stress strain on a graph here, we've got our standard bit where we've got our Hookean elastic deformation. So this bit here, this is going to be the limit of our proportionality. This is where we've got proportionality between force and extension. So that bit, limit of proportionality. You could, beyond that, it's no longer a straight line. Sometimes you can get a little bit of give before you actually get beyond the elastic limit. So, I mean, you haven't varied much from a straight line. Sometimes you get, separate from the limit of proportionality, you get an elastic limit where it will return back to its initial position once it's become slightly non-Hookean. And then after that, you can get some interesting shapes. So it might do something like this. This is the usual graph that people draw out. So you might get what's called yield points. So from the top here down to this low point here, you can see essentially we're just getting this free extension, where for the force that's already been applied to get up to this yield point, we're just going to get this accelerated extension now, up until, well, even beyond this point. But these are often called the yield points. But I mean, this is getting a little bit beyond really what we need to describe in the behavior of these materials. But just for completeness sake, these are called yield points. I can't say I'm that well versed in exactly what's going on here, but the behavior of the material, like I say, you can get this accelerated extension. And then beyond that, you've got this high point here. This is the maximum stress, the most pressure that you can apply. So the greatest force to some extent, depending on the area. This is your ultimate tensile strength. So this is the ultimate, so tensile, so for stretching, the ultimate tensile strength of the material. That's the most load it can hold. But of course, I mean, getting it up to that point isn't great because you've done all manner of damage to it. When you look at the extension that you've applied to this material, it's got massive extension at this point. It might be clinging on, but yeah, it ain't great. By the time you've got up there, okay, it is supporting that weight, but it's not doing it very long. It's not in a sustainable fashion, because now we're going to get another accelerated. We're breaking down now. We go past this. If you're maintaining that force, you're going to go over this hill, and we're going to get to a point where it's actually going to break. This is the breaking point when we get up there, which is the maximum strain that the material can take before it breaks. But if you're an engineer, you're not wanting to get into this crazy area. You're not wanting to be thinking, oh yeah, here's the ultimate tensile strength of this material, so let's load it up to the max, because it's going to start falling apart. This is not a sustainable construction that you've got then. So yeah, these are all of the key points of terminology on here. I wouldn't get too bogged down in all of this. Sometimes you get asked to draw these things, which I think in some ways is a bit unfair because it's not entirely obvious what these things really mean. This is a very complicated area of physics as to what's actually going on. So the key bits really are, we've got this main area of interest. This is where our Hooke's law and our elastic potential energy equations and things like that all apply. That is our proportional area. The force is proportional to the extension. That's our Hookean domain. That's mainly what we're interested in. And then we've got all manner of ways that the material starts breaking down from then on. It's then no longer Hookean. It's then no longer elastic, and we're getting into inelastic deformation. We've got these areas of accelerated deformation between the yield points, and then as we're coming up here to the ultimate tensile strength and then breaking. I mean, this is all of this is all inelastic deformation, which is not really what we're wanting to have our materials experience. So it's useful to be aware that these things exist, but really, if you're going to get a better understanding of this is where you'll be specializing in materials science and such like, if you start taking this to university level and beyond in your studies of physics. So there we go. That's Young's modulus. Yeah, we can see it's very similar to the force constant, and we've just made it more material specific. So that's the main takeaway in all of this.